And hello, we are on back to Exploring Creation with Physical Science, 3rd edition, looking at the student notebook book together and stumbling over my words. We're in module 10, and it's been a good week or so since I wrote all this up, so let me try to remember exactly what I was learning here. Okay, so electromagnetic waves, this is a definition. It's a transverse wave composed of an oscillating electric field and a magnetic field that oscillates perpendicular to the electric field. Okay, so I wrote this in my own words up here. So it's an electric field and a magnetic field, both oscillating perpendicularly to each other. What does that look like? Because I can't imagine. Well, here it is. I'm glad they gave us a diagram. So you can see that the one is going up and downy, and these are going sideways. So we've got vertical, horizontal. Those are perpendicular, okay? And the red are the magnetic fields. The blues are the electric field. Blues are magnetic fields. We've got our wavelengths that are still from one to the next, not hopping from one field to another, but between its own same fields. We have the direction of the wave. Wow, this is like really awesome here. Do you guys see this? We have our x-axis, we have our y-axis, it always goes up and down. And then we have our z-axis. Whoa, we're in another dimension now. And I just think this is fascinating. I do not pretend to be able to wrap my mind completely around all of it, but so I am just lead learner here. I am not a physicist or chemist. I'm just a mom trying to help my kid through their book, and love you, Ezra. This is your father's field. Boy, he did not understand math at all, he said, growing up until he hit college, got past his freshman year, and started in his sophomore year in calculus, and they started doing stuff like this right here, these waves. And it all hit home for him. He's like, oh my goodness, I understand math now. So, and he works as an engineer and uses higher level math, still struggles with basic math, and I'm the one who calculates the tip usually at a restaurant. But boy, he can just wrap his mind around things that I cannot. And this is one of them. All right, so this is the beginning, and I want to show you on page 351 right here a little bit about that. This is what's happening here. We've got a vibrating charge. This is an electrically charged particle, and this is the direction of the wave. This is a vibrating charge. Okay? So, what are electric and magnetic fields? What are they two aspects of? This is two questions. So, what are fields? Well, those electric and magnetic fields, they're charging fields that create an electromagnetic wave, which is all of this, electromagnetic wave. And they are two aspects of the electromagnetic force. Okay, we're on page 295, and sorry for the shadow. I'll do my best there. What do mechanical waves need in order to travel that electromagnetic waves do not? They need matter. They need matter. So the thing to go through. I'm not going to try to explain everything. It'll take too long. Explain electromagnetic radiation is the energy that is transferred by electromagnetic waves. If the electromagnetic waves go through matter, it loses some of its energy to the matter. But traveling through space, electromagnetic waves lose no energy. When electromagnetic waves travel far, their energy spreads out over a large distance. Think about the thermal energy coming from sunlight and rays of sunlight, and how when they go through, say, the windows of our house, well, they can be magnified if it's a magnifying type of matter. But when they hit the walls of my house, they are greatly reduced, and they might warm my attic, which has a thinner roof to go through, but my walls have insulation in them, and they don't get their thermal energy doesn't make it through very far. So that's matter slowing down. It's losing energy. It's absorbing the energy. That's just an example that I made up, and I hope I'm right. Okay. And that's just me doodling. Sorry about that. All right, so let's look at speed of electromagnetic waves, light. How fast do electromagnetic waves travel in a vacuum? Well, and I think this is their way of just kind of like setting a baseline so that there's no friction. There's just kind of, how fast can they go? Well, this is interpreted here for us. This is 670 million miles per hour. What? Or this many meters per second. 300 million meters per second. So, how does the speed of light compare to the speed of sound? Light is crazy faster than sound. This is how fast light is. 300 million meters per second in the air. And sound is only 340 meters per second, or 760 miles per hour. But you can see that 340 compared to 300 million doesn't hold a candle to it. Now, so light is faster than speed. The speed of light is faster than the speed of sound. Which is faster? Light. Yes, don't blink, you'll miss it. There you go. Light is faster. Good. What is the speed of sound dependent on? And that the speed of light is not temperature. If you might recall, we were always accounting for temperature in Celsius in our equation to determine the speed of sound. So isn't that fascinating? Never think about that, but I wonder if I go hiking in the freezing cold, if I'll hear like have a harder time hearing than if I already have a hard time hearing. I wear a hearing aid on one side. So I wonder, yeah, if compared to the heat. It must be true. All right, the substance through which it passes. What is the answer? That's the answer. This is like Jeopardy. The substance through which it passes, and you say, what is the speed of light what the speed of light is dependent on? That's the question. The speed of light is dependent on the substance through which it passes. All right, so that could be air. That could be a lot of things, right? All right, we're on 296, day 2. Let's see here. We're just going to go through half today. So nice and short, because last time was way too long. We're never doing that again. Sorry about that. All right, so wavelength and frequency. Explain some more doodles. More doodles. Sorry about that. All right, I'm a doodler. Explain the important points. Okay, so this is Wigton's notes on the section that I read on wavelength and frequency. And this is what I learned. You're welcome. We're going to learn some cursive here too. Speed is the same as, let's see here, same, but wavelength and frequency can be different. All right, so these two are inversely proportionate, proportionate, which means if this is graphed, wavelength and frequency, they would go, the graph line would go this way. As one gets higher, the other one gets lower. The other one gets higher, the other one gets lower. So that's inversely proportional. I want you guys to learn those mathematical terms because we use them a lot as you grow up. It's in math and in science, and let's see here, statistics. Used it a lot in statistics. Okay, so speed of light is what they refer to. What is C? And this down here, it is the speed of light, and it's any electromagnetic wave. Since speed is constant, if you know a wavelength, you can determine the frequency. So speed is constant for what? Well, we're talking about the speed of light. So it's like, what is this referring to? Speed is the same, meaning it's just a constant amount that we can count on. So we got right here that amount that we talked about earlier, and not to confuse you or anything, but on the page before I showed you meters per second, 300 million meters per second. Well, this can also be written out like this. If you could get it clear, you can see that's what that looks like in scientific notation. That's called, right? Scientific notation. So there we have it again. Did I write the same thing? I'm gonna go a second guess it. Yep. Okay. To the 8th. It's really messy, but it says to the 8th power. Okay, and so the c on this is speed of light, is what is equal to this. So also known as velocity. Okay, so we're moving on. Light is really individual particles of light all flowing in the same direction like a stream. Newton believed this and came up with this. Okay, so this is called particle theory. So you might want to know just the highlight of particle theory. Light is really individual particles of light flowing. And okay, one thing I need to point out is when I was reading this, it wasn't clear at first either, but I will make it clear to you, is that the particle theory of light was one of the first theories of light. It is not the truth of light. Theory just means it's what somebody believed. This is what Newton believed. Okay, so we're going to keep going here and see what's actually true. Okay, so particle theory was the theory, I should have presented it this way, that light is just individual particles flowing in the same direction like a stream. Okay, wave theory, you're going to have to learn lots of theories in life. This is just part of life. Okay, so wave theory, even if they're wrong, I cannot pretend to know how to say this name, but we're going to say Christian Huygens, I don't know, contemporary of Newton. He disagreed with him and said, no. It's a wave. Light is a wave. And by the early 1800s, most scientists agreed with him. All right, we're going to take a pause on the theories, come back to it in just a minute, and it asks, how does the text define interference? The interference is defined as the interaction of waves with other waves. So here's a wave happening from a raindrop. It kind of is happening, like, just pretend there's multiple drops coming down in the same exact spot, because that doesn't make sense otherwise. Okay, so drop just happened, made those ripples, and another drop had just happened same time and made those ripples, and they're interacting. So right here is called interference. Interference, see it? Zoom in on the interference. Okay, good job. Let's move on. All right, textbook 354. You like my notes to myself here because I know I forget stuff. Okay, so page 354 says don't use this here because there's an error. They would never make an error in this book, ever. So no, just kidding. It's okay. We give them grace. So don't look at the book or the student notebook for this. Look in your textbook. It's perfect. This is what we want to look at. And this is how we know they made an error, is because they have the same exact thing for constructive interference versus destructive interference. Same patterns. Over here we have that one, which is supposed to look like that for constructive interference. And then we can see that destructive interference looks completely different. So that's correct. That's what we want. Okay, so you can see before interference, there's two ripples coming together, one from one droplet, one from the other, and they're just about to crash. They crash, and they make this giant, cool, big wave with much higher amplitude, right? And then afterwards, they bounce back again and swap places, whoosh, and they go the other direction. Well, they keep going, actually. They just keep going. They don't bounce back. They just keep going right through each other, and with a giant wave in between. Okay, so that is constructive interference, which happens at certain types of timings. All right, so destructive interference happens in different timings and types of waves here happening at the same time. All right, so this one, we've got A coming this way, B's down below this time, there's a trough instead of a crest, and they come at each other, and what happens? They cancel each other out. What? And then they keep going just like the other one did too. So A keeps going this way, B keeps going this way, and they keep on going on their way. But for just a second, instead of making each other bigger, they completely cancel each other out. Fascinating. Now I read, let's see here. Oh, I wrote here that I wanted to read this, but I just summed it up for you. So we're good. Okay. In 1801, English Thomas Young showed that light was a wave. So page 355 diagram. Oh, I love this diagram. This is awesome. I'm going to put it up here. It's worthy of the music stand. Okay, so here's the diagram. Hold it still, Mrs. Wigton. Hold it together. All right, so we've got, come on, focus, focus. Wave theory. This is the idea that if this is the light source, it goes through here. The light is shown through these bars that are set like this. The wave theory says I should see, is this not, is this the one? Yes, the wave theory should show this pattern right here, okay? And if the particle theory is true, this is what should happen. If light is made of particles, I should only see 2 lines of light on the back wall, not all these stripies from all the waves, right? Well, here's what happened. They did the test and they got all the stripies. So they said, ho, 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 we have proven it is a wave. It is a wave. Light is a wave. Newton was wrong. Huygens was right. Wow. Little did they know, told much later, that we have a whole nother science experiment to do to prove that there's a third way. Isn't that just the exact thing that Jesus would do? He'd provide a third way. Here we go. All right, so we've got the photoelectric effect. What is happening here? Hertz, Mr. Hertz, Heinrich Hertz in 1887, he discovered something puzzling. He discovered that, I'm going to just read this so that I don't get it wrong here, that when the blue light hit the surface of a metal, electrons were emitted. The brighter the blue that hit the surface of the metal, the more electrons were emitted as shown. So just a little bit, boop, with a lot of it, whoa! All right, and then the interesting part was that if bright red light hit the surface of the metal, no electrons were emitted, none. This is called photoelectric effect. So this is metal, this is different colors of light, and they're measuring the amount of little packets of electrons coming off of them, okay? So they couldn't understand it. And so they're like, we've proven something we don't get. But thank you for giving us a crazy smart person in the world. Albert Einstein, that God provided to us in 1905, proposed a new theory often called the wave particle theory. And those little electrons are called packets of energy called photons. Photons. So those were photons. And he said that they don't represent a fixed amount of energy. It depends on the electromagnetic wave. Greater the frequency, the more energy each of its photons has. So blue light has a higher frequency than red light. We'll look at that again later. So it was putting out more photons. Here's a cool picture of what they actually figured out. Check it out. So instead of it just being waves or just being particles, this is the wave particle theory in action right here. So you can see that those are actually, they're all the wave, it's more wave, but then every one of those light beams is made up of particles, little photons, if you will. So isn't that amazing? I just think it's amazing. All right. So it kind of goes over here a little. I'm going to show the picture. I'm not going to pretend to understand this completely. But it says when an electron returns to a lower energy level, a photon particle is released and travels like a wave. Isn't that awesome? So it shouldn't surprise you. This is called the quantum mechanical theory of light. And this is currently accepted theory on the nature of light. I'm reading right here. Since this light can be, consuming or confusing, let's sum it up. Light is composed of little packets of waves. Each individual packet can be thought of as a particle called a photon. At the same time, however, since each packet is composed of electromagnetic waves, light can also be thought of as a wave. Thus, light will sometimes behave like a particle and other times behave like a wave. Since waves within a photon are electromagnetic, there's no need for atoms or molecules in order for light to travel. As a result, light can travel through any region of space regardless of what occupies that portion of space. Woohoo! All right, moving on. Let's see here. So we talked about all of that. I already talked about all of that. Photons are packets of energy released from electrons. All right, I already talked about Einstein's theory, and we're going to come down to the on your own questions, okay? So what produces an electromagnetic wave? There's lots of questions here. Start with that one. The vibration of an electrical charge, like an electron, produces the electromagnetic waves, which are EM waves, okay? What do all electromagnetic waves have in common, and what makes electromagnetic waves different from one another? Well, they all have the same speed, but they differ in frequency and wavelength. Boop, wavelength. All right, suppose a photon is traveling through the air. I'm going to suppose this in my mind. If the particle suddenly hits a lake, what will happen to its speed? Woo! Splash. All right, speed of light in the air, 300,000, was it meters per second? And then in water, according to, how does Mrs. Wigton know all this? All right, let me tell you. Because it was on, I'm going to find it here. Speed of light in certain substances table 10.1 on page 352 in the textbook. Oh, that's cool. We should look at the rocket launch. That's awesome. It says, if you've ever been to a rocket launch, you experience a difference between light and sound waves. You will see the rocket launch before you hear its rumble. It sounds like the sound hitting Mach 1 faster than the speed of sound, too. We were talking about jets the other day. Okay, table 10.1. Speed of light in certain substances. Here we have it in air. Constant speeds here. Alcohol, fresh water, acrylic, plastic, crown glass, flint glass, diamonds. Wow. Okay, so where's the water? Water, 220 million meters per second. So the difference between the two is one is faster than the other one. So when it hits the water, it slows down. That's the answer. Okay, 10.3. How does photon energy relate to frequency? What experiment first showed this? They love to ask multiple questions. All right, so photon energy and frequency are directly proportionate. This is the opposite of the inversely proportionate. So directly proportionate means as the one gets bigger, the other also gets bigger. So the graph looks like this, okay? Directly proportionate. I didn't answer the question. Which experiment first showed this? I better go look it up. I don't remember the answer. Just a second. I'm going to pause you. Oh, right. The answer is in the photoelectric effect experiment where that looked like this, okay? So the electrons hitting the metal, or the light hitting the metal, and the electrons and photons coming off, okay? So we're going back to our study guide, and this is my favorite part of this module so far. The electromagnetic spectrum. Okay, I did fill this all in, but do you know what? They've got a much better picture in the book, so we're going to look at the book. All right, so down here we've got, look at this. This is fascinating. All right, so we've got radio waves, microwaves, infrared waves, visible light, ultraviolet light, X-rays, and gamma waves. Do you see how the wavelength gets bigger, or not bigger, smaller, and the frequency gets greater? So this is inversely proportionate here over this spectrum, okay? So what can we say about each of these? Oh man, we go into it in just a minute here. So it says make notes about each one as you read them, okay? So there's temperature of bodies emitting those wavelengths. Whoa. That's really fascinating. Okay, here we go. First section, radio waves. These are examples. You can see TVs and radios and cell phones. Oh my, here we go. They have the longest wavelength and therefore the lowest frequency. It looks like that. The range short of the wavelength is short as a football and to longer than a football field. And here's the little, like an example of an AM radio wave. FM radio wave gets a little more in frequency. And TV waves, whoa, it gets even faster. All right, but not that fast because then we have to move up to microwaves. These have some of the shortest wavelengths. Why I'm confused why they say that there when we've got all those ones that are even shorter wavelengths over here. So I'm trying to figure out why they say that in the book. Let me see here. Oh, shortest wavelength radio waves. I should have written more details here. Shortest wavelength radio waves. Even though they're just microwaves. They do weather radar, GPS systems, microwave ovens. The wavelength in microwave ovens are absorbed by water molecules in food, and this makes the H2O molecules spin, causing friction in the food and therefore heat. The heat cooks the food. I heated up something in the microwave the other day, and I noticed that my bowl was hotter than the food inside my bowl, and I realized it was chili, that there wasn't a whole lot of water in the chili, and so by adding a little bit of water, mixing it in, it heated up much more efficiently in the microwave. All right, we're at infrared. Sorry, I'm not holding it still very much there. Okay, we'll try to get it all in. Below red, infrared, below it, remember infrasonic or infrasound. Yeah, we just did that in the sound waves, and that means below. So it was the lower frequency than red is what that means, infrared. I just said that there. I wrote it down too. When a hot object gives off heat, most of the energy is in infrared light form. For instance, a space heater. Well, by George, our power's out and there's a space heater. You see it? Right there. Space heater. That is infrared. Food warming lights at restaurants, reptile lights in zoos. A thermograph can make an infrared map. And thermographs can be used to search for, like for search and rescue missions. And those really creepy movies that like look like they're gonna hunt you down in the dark. Anyways, we don't watch those. Visible light. All right, so we've got some color here going on. It says see diagram 10.7362. We're gonna do that. So, oh, I love this. There we go. This is awesome. Here we go. So check it out, visible light. And I'm gonna try to keep this in focus. We have the wavelength of red, orange, yellow, green, blue, indigo, and violet. And then higher than violet rays or ultraviolet, lower than red wavelengths of waves are infrared. These are the ones you can see. These are less visible, if not at all. And they say that don't memorize these numbers. You don't need to know the exact wavelength in nanometers for each one of these colors. But what would be really, really good and helpful is to memorize red, orange, yellow, green, followed by blue, indigo, and violet. It's a rainbow just for you. Thank you, Cat in the Hat. This order will help you remember that the highest wavelength was red. If you can remember Roy G. Biv, ROYGBIV, that will help you remember that the last ones had the lowest wavelength, the first ones have the highest. And so if you remember the order, you've got yourself the order of wavelength as well. Isn't that awesome? So, let's see what's left here. Ultraviolet, above violet. Okay, because ultraviolet light has frequencies higher than violet light. We already said that. More energy the wave has, therefore, the ultraviolet light has more energy than visible light. So it can kill living tissue, sterilize surfaces. It can cause cancer, and damage your eyes. We've got another picture to look at here. I thought this was really good. So we've got different kinds of ultraviolet light that come from the sun, and they hit, there's our moon, and there's Earth. We've got an ozone layer around Earth that's protecting us, and it keeps out the ultraviolet C, ultraviolet B for the most part, but A gets right through because of its wavelengths probably, and it can be damaging. It's also it has really good properties too, just like everything can be potentially good or bad, right? And so we went to just understand that it says the kind of light the Earth needs, visible and infrared, is allowed to hit the surface of the Earth. And that's why we need, what we're getting from it is light and warmth. We're getting just the right amount of warmth from the sun so that we don't freeze to death here on Earth, and not too much so that we don't burn up. It's just really perfect, and God planned everything out in that way. All right. X-rays. They have a very short wavelength and high frequencies. They can pass through soft tissue, but not bones and teeth. So X-ray techs put on a heavy lead apron on you, and they stand behind a lead barrier before dental X-rays to protect you and them from X-ray exposure. So it passes through some things, but not hard bones and teeth and stuff. Gamma rays have the shortest wavelength. Woo, look at that. Shorter than the diameter of the nucleus of an atom, and the highest frequencies. They're very dangerous. Radiation therapy is used to target and kill cancer, so it can be used for good, right? It can help kill cancer, and give you be used to make brain scans. They're done with gamma rays, but this can also kill some of the good things in us too. So, all right, I think this is the end here. 10.4 says, without looking, what is your colors? And put these in order. Kind of have the answers here, but I have no way of quizzing you. So if Roy G. Biv are the colors, they have yellow, indigo, red, and green. Green followed by blue, indigo. So that's the order right there. And finally, radio signals are really made up of electromagnetic waves. Why doesn't a radio station's antenna glow when it transmits its signals? Well, because the light it emits is not visible. Radio waves have wavelengths longer than visible lights. So on that fun note, think about all the waves traveling through the air that we cannot see or feel and really just benefit from. It's so cool. I will leave you now. Have a wonderful rest of your day. Take care.